Lesson 2 today, we'll be talking about additional identities and simplifying trigonometric expressions. So first and foremost, we should probably define exactly what an identity is and what we're going to be doing with them. So first here you can see on the notes page, if you printed it, an identity is an equation that is satisfied by every number for which both sides are defined. When and where are we going to use these? Basically, we're going to be using them in the simplifying process that we're going to go through today. And the goal there is to really get it down to the smallest number of terms. If we can get it down to a single sine of x, or even sometimes we might get out just a number as our simplified version. That's what we're really looking to do, because ultimately bullet point 2 there, it makes the math problem look prettier, but it's also easier to use. If you look at some of the problems that are already on this page, if we had to plug in multiple x's versus only plugging it in once, that's going to make our lives a lot easier. Before we get into the examples on this page, there are 2 additional identities that we're going to tack on today that we're going to be looking at, in addition to the Pythagorean identities and the reciprocal identities that you learned and reviewed about in lesson 1. So remember that we have the 2 functions, tangent of x and cotangent of x. And you may recall this from when we were talking about the unit circle, but tangent and cotangent can be written in terms of sine and cosine, which we'll find later that that's really super important for us. We like seeing sines and cosines. Tangent is the fraction sine of x over cosine of x. And because tangent and cotangent are reciprocals, that means that cotangent is the fraction cosine of x over sine of x. So when we're working through a problem, if we see sine of x over cosine of x, we can replace that with a simple tangent. Okay, so instead of working with a fraction, we just have that one trig ratio. So let's take a look at our first couple examples here. The first one says we are to simplify 3 sine x times cosecant x. So what we want to look for is getting this down to a single trig function if possible. Right now I see 2 different ones, and perhaps in your mind you're thinking, well, wait a minute, sine and cosecant, they're reciprocals of one another. So I could change this to 3 times sine of x times 1 over sine of x. And that's our reciprocal identity. All right, and then perhaps what I could look at next is when I'm multiplying all 3 of these pieces, really, I can multiply across the top and across the bottom. So this is really 3 sine x over sine x. All right, so multiply fractions. And because I have sine x over sine x, well, that's just like 2 over 2 or negative 7 over negative 7. We are allowed to cancel those out, which means the final answer here is just 3. So what started as 3 sine x cosecant x ended up just being a simple 3. And what we could write for the last one stepwise would be just simplify fraction. We had common terms top and bottom. And you don't have to write these steps that I'm writing here. You're going to see as we work through this unit, depending on how the question is asked, they might ask you to do that. They might do something later where, they give you some steps and you have to fill one in, or you have to identify if something was done incorrectly, that kind of thing. But really what this should kind of look familiar to is like a 2-column proof. What you would have done back in geometry, where, on the left-hand side here, we're kind of working down the problem. Now, they didn't give you the prove statement in this case. Eventually they will, okay? But for these first couple, it's pretty straightforward. There's not too many steps. It would almost be a giveaway if they gave it to you right away. But then over on the right-hand side, these are our statements that or the reasons rather from a 2-column proof. So why we were allowed to do each of the steps that we did within the proof. So we're kind of using that same concept, but again, we're looking at it from a trigonometric perspective. And what you saw in the lesson on Friday is that, for example, in this one, we had sine of x over sine of x. That's similar to like a rational expression type of deal. So those concepts that you've been learning all throughout your mathematical career are all going to come into play here and there throughout this particular section of our unit. So be prepared to, really be looking back at things that you already know, but looking at it again from a trigonometric perspective. So let's take a look at example 2 here. So it says simplify tangent of x times 1 over cotangent of x. So there's quite a few different things that I could actually do to get this one started. Perhaps you're thinking on this page we wrote that tangent of x was sine over cosine, and cotangent is cosine over sine. You could certainly start there. Another tactic, and the one that I'm actually going to go with here because it's a little bit faster, is to change, since tangent and cotangent are reciprocals, I'm going to change them both to, in this case, tangent. So tangent of x, I'm not going to do anything with at the moment, but cotangent is the reciprocal, so 1 over cotangent would just be tan x. Now, if we ignored the tangent for a second, if this were just x times x, think in your head, what would that equal? Well, hopefully you were thinking x to the power 2, x squared. Well, we can do the same thing here. We're doing tangent x times another tangent x, so we can put this together and make this a tangent squared x. Basically, if we wrote steps here, I'm not going to, we used reciprocal identity for the first one, and then the second one is really just exponent rules. It's your multiplication rule where you're allowed to add exponents. All right, moving along. The next example one, we already did one, but the next example here, we're supposed to simplify 5 sine of x over cosine x. Again, what do you notice straight out the gate? Thinking about your Pythagorean identities, your reciprocal identities, and the new ones, the tangent and cotangent. Well, what jumps out at me is that we have sine over cosine, and sine over cosine we just learned here is tangent. So I'm simply one step going to rewrite this as 5 times tangent x, because this portion of the fraction is that tangent cotangent identity that we have at the top of this page. Over here to example 2, we're supposed to simplify cotangent x times sine of x. So again, what do you notice? I see cotangent x, couple options we have there. Sine of x, I could change that to cosecant if that would be helpful here. I don't know that it would because I don't have another cosecant. But since I know that cotangent has an identity that involves sine in it, I'm actually going to switch the cotangent using that tangent cotangent identity. So that would be cosine of x over sine of x. Again, we're going to leave the sine of x alone. And now what do you notice? Well, by tweaking that, if it helps, you can always write a non-fraction over 1, to put it in fraction perspective if that's more applicable for you. But what you should notice now is that I have a sine of x in the top and the bottom, so I'm allowed to cancel those. And this one actually ends up being just cosine x. And again, if we were to write some steps, we'd say that that was cotangent, tangent identities, and then really it was just cross-canceling or simplifying the fractions again. All right, example 1 for the third time. So we're supposed to simplify 1 plus cotangent squared of x. Now, when I see that squared sign, immediately my brain goes to Pythagorean identities because all 4 of the other examples did not have a squared term in them. So that makes me think that this one's going to use something slightly different. The other thing I notice is that we've got a 1 and a cotangent squared together. And if I look at my notes, or if you have your formula sheet, the Pythagorean identities, there's one that's written 1 plus cotangent squared x equals cosecant squared x. So this one I can simply just rewrite in the form cosecant squared x because of Pythagorean identity. I'm just replacing basically the left-hand side for the right-hand side because now I only have one term versus 1 plus cotangent squared was 2. All right. Last one, I would suggest maybe pausing the video based off of what we just did, give that one a try, and then jump back on when you are finished. Okay, so if you were daring enough to try this one on your own, maybe you figured it out, maybe it was a little bit of a struggle, but I'm hoping that, again, Pythagorean identity jumped out at you because of the 1 minus cosine squared x. The problem is that that's not the way the Pythagorean identity is written on your formula sheet. The one that you learned was sine squared of x plus cosine squared of x equals 1. So are they trying to trick us here, or is this actually Pythagorean identity in disguise? Well, in this case, in our example, the 1 and the cosine squared are together. So what I'm going to do is I'm going to come over to our Pythagorean identity, and I'm going to get this cosine to the side that has 1. So to do that, I would subtract the cosine squared over. And that means that sine squared of x equals 1 minus cosine squared x. So what I am able to do now is I'm going to leave sine of x alone out in front here, but I'm going to rewrite the 1 minus cosine squared x as its Pythagorean identity trade-off, which is sine squared x. Now here again, this is like a previous example. We have sine of x everywhere. If you think about it, this one has a power 1. We don't typically write it, but it has it. So what we're able to do at this point is, again, use our exponent rules. So not even trig relatable. We can add the 1 and the 2, and we get sine cubed of x. So again, we're looking to dwindle it down as much as possible, get it to look a little bit cleaner, maybe get it down to a single term, as has been the case for most of these. But that's our goal with these kind of more simplifying problems. All right, so let's take a look at